Okay, so welcome back, everybody. I posted the announcement before lecture about MATLAB use, and I mean this applies not just to MATLAB, but whatever computational means you use, because one of the purposes of this course is to give you problems that are maybe more realistic looking in terms of what you might see. Obviously, a lot of the matrices involved will be smaller when I want you to see the underlying workings of a thing. But for instance, one of the problems on this homework involves a larger matrix, not large in the sense you might encounter out in the wild, but something that you typically wouldn't handle just with by hand calculations. So it is not just allowed to use MATLAB. It is encouraged for you to do that. I don't want you dealing with that by hand, even if you theoretically could. So just make sure that you include all of the work you did published as PDF or just in a nice readable form. That's what I meant by don't send raw M file. Of text. It's nice to see it in good readable form so that the grader doesn't get too mad at you. So anyway, okay. So we ended off with a question of, so we're still doing Leontief input-output models, and the question was instead of fully inverting the matrix in question, right? So we had this I minus m times p is equal to d, right? This was ultimately what we were looking at. And the question is if we are in this situation where this is invertible, so that we know that this unique solution is I minus m inverse times d. Computationally speaking, what if, for a variety of reasons, we don't actually want to find the full inverse here, and the question, I haven't asked a question yet here, which is, what if I wanted to just compute individual entries, right? How can I compute individual entries? And if we're calling this matrix A, how can I compute individual entries like A sub ij in this matrix A, which is I minus m inverse, rather than computing the entire inverse? And our answer to this was the adjugate formula. This is one way of doing it. And you might say, well, isn't it just better to have the full inverse? And the answer is yes, it is, of course, because you can read off the entries if you have the full inverse. But maybe the thing you care about is actually just one or two or five entries of the matrix rather than the whole thing, right? And again, imagine now that this is big. Imagine this is like a 100 by 100 matrix, and you'll see what I'm saying here, where maybe the question you're asking or the thing you're really trying to get at is only like one or two or a few entries in this matrix rather than the full inverse. And so that's the idea, right? So what is the adjugate formula? So recall from yesterday's lecture, we had this definition of the ijth cofactor, which is minus 1 to the I plus j times the determinant of a sub ij. A sub ij being this n minus 1 by n minus 1 matrix obtained from A by deleting its ith row and jth column, right? So for a 3 by 3 matrix, this is going to be a 2 by 2. For a 2 by 2 matrix, these are going to be 1 by 1s. These are going to be 1 by 1 matrices, which we call scalars, right? The adjugate formula is this statement, which is A inverse can be written as 1 over the determinant of A. Remember, this is a scalar, so it's this scalar, 1 over the determinant, times the adjugate of A, where the adjugate of A is the matrix of cofactors where the entries are swapped in the sense that the ijth entry of the adjugate matrix is C sub ji. Okay, so this can be a little bit confusing the first time you see it, but this is how this works. So this weird thing that we do in remembering how the 2x2 inverse formula works explains what it is that goes on here. So I encourage you actually to verify that the familiar 2x2 formula for the inverse of matrix satisfies this. This actually just is the adjugate formula. Okay, so another way of writing this is to say that the ijth entry of the inverse of a matrix is -1 times, or -1 to the j plus I times the determinant of A sub ji, which is the matrix obtained from A by deleting the jth row and ith column, divided by the determinant of A itself. This is what we're actually going to use to compute this entry by entry. And a way of writing this in a more expanded form is to say A inverse is, this is just me rewriting the adjugate formula again. Okay. So all of these are equivalent to the adjugate formula that I wrote on this page. Right? So this adjugate formula is exactly both of these two things. Okay. And just to remember why we might be interested in doing this like entry by entry, recall the facts from yesterday, which stated that in this matrix that I'm computing the entries of, this I minus M inverse, if external demand for sector J changes by +1, then the columns of J indicate how production must change for in all sectors to compensate. Specifically, if I'm looking at the ijth entry, if the external demand for sector J changes by +1, then the ith entry of the jth column of I minus M inverse indicates how production must change in sector I in order to compensate. And so the type of question that I might ask, showing you that I might only be interested in a single one of these entries, or maybe a couple of these entries, is maybe the question that you want to get at is asking how much the production in a single sector needs to change in order to compensate a change in external demand. We know that we don't have to do this by +1. We can do this by +k and just scale those entries, since those entries scale by k in order to answer this. And so being able to compute the individual entries of this matrix tells me that I can answer questions about how the production in any given sector must change in order to accommodate an increase or decrease in external demand in one of the other sectors, right, or the same sector. So that's why this is so useful, because ultimately maybe those are the sorts of questions that I really care about answering for these models. Okay, so that's the idea here. Now, all right. So let's see how this works in an example. So that pen is almost out. Let's consider the consumption matrix. Which is, reading row-wise, this is the matrix M, which is 0.10, 0.15, 0.12, 0.20, 0.30. We've seen this one before. 0.25, 0.4, and 0.20. There's our consumption matrix M. And let's ask the question. Suppose the external demand for sector 3, which means this is the external demand for product 3, changes by +1. How must production in sector 2 change? Now again, you might look at this and say, well, this is 3 by 3, and I've actually already found I minus M inverse for this problem, so I can just look at that matrix and circle the entry, and that's true. But what we're doing here is showing how this adjugate formula could be used for any of these problems, not just for a 3x3 problem. Okay. The answer to this question is completely answered by what entry of I minus M inverse? Well, I'm looking for what has to happen, what has to happen as far as the production in sector 2 if the external demand in sector 3 changes by +1. So this value is stored in the row 2, column 3 of I minus M inverse. So it's stored in the row 2, column 3 entry. Okay. Now, in order to compute this using the adjugate formula, and specifically the form of the adjugate formula I'm going to use is I'm going to be looking for the ijth entry of A inverse here. Right, let's write out what I minus M is. So I minus M, as we've written before for this matrix, is, again, I'm just reading row-wise here, so this would be 0.90 minus 0.15 minus 0.12 minus 0.20 1 minus 0.30. This is bothering me. I didn't put the 0 there. 0.25. Sorry, minus 0.25. All this is minus. Minus 0.40 and minus, actually no, this would be 1 minus 0.20, so this would be 0.80. Okay. There's our I minus M. Call this A. So then the thing that we want to compute is, maybe I should write it like this. This is confusing to write it like this. So let's write it like this. I want to compute A inverse 2, 3, meaning the 2, 3 entry of A inverse, the entry in the second row and third column. According to this, I'm just going to flash it on the screen one more time here. This A inverse of ij is minus 1 to the j plus I times the determinant of A sub ji over the determinant of A. So that by the adjugate formula, this is minus 1 to the 3 plus 2 times the determinant of A sub 3, 2 divided by the determinant of A. Now we're calling this I minus M A, so we compute its determinant, and we also compute the determinant of A32. What is A32? So first of all, determinant of A32 is the determinant of what matrix? So A is a 3x3 matrix. A32 is a matrix obtained from A by deleting its third row and second column. Okay, so this is a 2x2 matrix. It is this one. So I'm deleting third row and second column. So this is 0.90 minus 0.12 minus 0.20 minus 0.30. Determinant of a 2x2, of course, I know how to find here. This is 0.9 times minus 0.3 minus minus 0.2 times minus 0.12, which if I do this all the way, this is minus 0.2940. Okay, so that's my determinant of A32. what is the determinant of A? A is a 3 by 3. So not so bad. Obviously, when you're using, computational tools, even if your matrix is absolutely gigantic, computing determinants, there are ways that software deals with computing determinants of very large matrices. It's not cofactor expansion, as I've mentioned. This is computationally too intensive. But there are ways of doing it. So here, determinant of A. This is a 3 by 3. We don't need to worry about any of that. I can just directly compute the determinant. There's no zeros or anything, so that I don't have to choose going down another row. I'm just going to go across the top row here. So this would be 0.90 times the determinant of the 2 by 2 submatrix, deleting the first row, first column. So this would be 1 times 0.8 minus 0.3 times, minus 0.3 and minus 0.4. Maybe I'll put brackets here to indicate this is the determinant of this 2 by 2 submatrix here. Minus 0.15 times the determinant of 2 by 2 submatrix, deleting first row, second column. So now this would be minus 0.2 times 0.8 minus, this would be minus 0.25 minus 0.3. I'm running out of room here. It's minus 0.3 here. Plus, this would be minus 0.12 times the determinant of the 2 by 2 submatrix here, where I delete the first row again and third column now. So this would be minus 0.2 times minus 0.4 minus minus 0.25 times 1. Okay. And so this gives me, if I compute this gives me a 0.5372. So what is our answer? This is, going back up here, this is minus 1 to the 5, so that's minus 1, times the determinant of a sub 3, 2, which we found to be minus 0.2940, divided by 0.5372. And what this is 0.5473. So what does that mean? So computing this means that if external demand in sector 3 changes by +1, the production in sector 2 must change by that amount. To accommodate. This must change by plus 0.5473 in order to accommodate completely this change in external demand. Obviously, there was nothing special about the 2-3, or sorry, the 2-3 entry in this, so I could have chosen any entry you like there to have done this. Again, remember, yes, in this case it's 3 by 3, so it's a small matrix, but you could do this, right? You could use this aggregate formula to compute individually these things in a straightforward way, and it doesn't substantially matter what the size of A is here. Okay, so yes, there's the issue of your computing determinants. One's an n minus 1 by n minus 1 determinant. The other one is an n by n determinant. But generally, you are happy to do this if the info that you need is in one or a couple of entries, rather than finding the entire inverse. Okay. Now, remember, this whole discussion kicked off because we were skittish about talking about a matrix inverse so flippantly when the notion of like actually needing to compute the thing came up. So you might be wondering, okay, well, what other computational tricks or even like theoretical tricks could I bring to bear on matrix inverses? And so another way of dealing with matrix inverses. Recall geometric series. What do I mean by that? What if I have the following thing? So I have a power series, but it's laid out like this. Well, my geometric series sum formula, right, owing essentially to Archimedes, is this. Now, this wasn't always the case. This was if the absolute value of x is less than 1, or the modulus of x is less than 1. This is what we get. Now, there's something to talk about here. So maybe it's more, maybe you say, okay, yeah, I remember my geometric series sum formula. In fact, you could also do this starting from any particular, you could start at the x squared term here. You don't have to start at 1. This is what you get if you start at 1. If you start at the x squared term, it changes what the numerator is, but ultimately this is what you get. So this is how geometric series work, but let's ignore that for a second and just look at formally how to do this. So what do I mean by that? What I mean by formally is I'm not going to worry about like notions of convergence of power series or any kind of thing like that. So what I'm going to do here is I'm going to say, I'm going to start with this expression. And so on. And then what I'm going to do, just to have fun here, I have just this expression sitting in the void, right? And what I'm going to do is I'm going to multiply this expression. Yes, it's an infinite expression. It's an infinite sum. That's fine. I don't care. I'm going to multiply that by 1 minus x. What happens when I do that? So what do I get? So, you might be tempted to say foil, right? We don't like foil around here because that it's really like a binomial thing times a binomial thing here, right? What you're meaning when you're thinking that is this distributes obviously across this sum. There's 2 big sums that result. There's 1 times this whole thing, and then I add to that minus x times this whole thing. So what I'm going to do is 1 times this whole thing. I know what that looks like. That's 1 plus x squared plus x cubed plus x to the 4th and so on. That's 1 times this. But then what about the minus x times this? Well, let's just see how that goes. Minus x times 1 is minus x. I'm going to put that here. Minus x times x is minus x squared, so I'm going to put that here. Minus x times x squared is minus x cubed, so I'm going to put that here. And so on. This would be minus x to the 4th. and so on in that fashion. So that when you multiply this out, these all cancel, and what I am left with is 1. Let's rewrite this equation that I just wrote. One minus x times 1 plus x squared plus x cubed and so on is 1. Oh. Divide both sides by 1 minus x. Now you might say, wait, you just showed this and you didn't even talk about this. So yeah, this is what it means by me calling this a formal proof. I've been a little bit hand wavy with what x is, what values x is taking on, what is going on here, but don't worry too much about that. This is showing you that like the structure behind this underlying fact is strong, okay? So this quantity really wants to be this this quantity is a way of thinking about it. But this is so this is what I got. Okay. Now how does this help me? Rewriting this ever so slightly. 1 over x, I could write that as 1 minus x inverse. And so 1 minus x inverse is 1 plus x squared plus x cubed and so on. And it's this form that this takes that gives me an idea, right? It gives me an idea. I wonder what idea that's going to give me, especially given that I have been discussing quite frequently in the last couple of days this. Okay. So here is the fact that I'm angling toward, which is the following. So fact: under certain conditions, I can actually write I minus m inverse. Notice I plays the role of the multiplicative inverse 1 here. This is a multiplicative inverse of a matrix, and that is 1 plus x squared plus x cubed and so on, which is I plus m squared plus m cubed plus m to the 4th and so on. Maybe you could say under what conditions. The conditions we'll talk about are for a square matrix M. So under certain conditions for this square matrix M, this is what we have. Now I can actually rewrite this in the same way that I rewrote this formally when I was doing this proof here. I can rewrite this as fact. This means if I track this, I have I minus m times I plus m squared plus m cubed and so on is equal to I. That's what that should mean, right? Notice this is me writing this statement. Or just going back to my original thing, it's me multiplying both sides by 1 minus x or 1 minus m here. Okay, writing this in a more convenient manner. This is me saying that I minus m times the sum from k equals 0 to infinity of m to the k is equal to I. Now, dealing with an infinite sum here, of course, I can view this as a limit of finite sums, so that I can view this as follows. I can say, well, this is really me taking a limit. The limit is n goes to infinity of I minus m times the sum k equals 0 to n of m to the k, and that is equal to I. Now, this I minus m term doesn't depend on n at all. I can actually view this as I can move this inside and distribute this thing to get the following. This is the limit as n goes to infinity of what? Of the sum from k equals 0 to n of m to the k minus m to the k plus 1. And that has to be equal to I. This means that the limit as n goes to infinity of expanding this thing. What do I get here? I notice that this is a telescoping sum. So wow, now we've had experience already with our two favorite types of sums, right? Basically, the only two sums we know, if we're not doing some Basel problem type thing, the only two sums we know how to actually sum are geometric sums and telescoping sums. So geometric series, telescoping series, these are basically the only ones we can actually sum here. So this is a telescoping series. So what does this look like? This would be m to the 0 minus m to the first plus m to the first minus m squared, and so on, in such a fashion so that the very last thing I get is m to the n minus m to the n plus 1, and that is equal to I. This sum telescopes in this way so that all the intermediate terms cancel, including this one, as it cancels with the m sub n coming from the n minus 1 term in this sum. Okay, or sorry, the minus m to the n coming from the n minus 1 term in that sum. And so what I get here is then the limit as n goes to infinity of I minus m to the n plus 1, and that is equal to I. But this I doesn't depend on n, and so what I get here is I minus the limit as n goes to infinity of m to the n plus 1, and that is equal to I. Subtracting I from both sides here tells me that this limit actually has to be 0, right? Or just looking at this equation tells me that this limit has to be 0. Of course, M is a matrix, so what does 0 mean here? This means it has to be the 0 matrix, right? So, you know how we said under certain conditions? Well, this is the condition that guarantees it, right? So this is the condition that guarantees that this is the case. Now, how do you verify this? That's a tricky one, right? This is a limit that might be rough to get at for some generic matrix. Imagine M is a very huge matrix. This doesn't seem like a nice thing. So there is another way that I'm not going to prove why this is the case. So I'm going to write one more fact here. Fact. This limit is 0 if and only if The largest absolute value of all the eigenvalues is less than 1. Okay. It turns out that this is true pretty frequently. For realistic consumption matrices. So it turns out that actually, for realistic consumption matrices, this isn't too much of an ask. Okay. Now, if, in addition, the entries of M are small, and M is sparse, or sparse enough, so remember what I said by sparse here. Sparse for a matrix means it has a lot of zero entries, right? What exactly a lot is, or whether the amount of zeros in the matrix counts as a lot for you, might depend, okay, on the context, but this is what we mean when we say sparse. What this sum that we have written for computing this inverse converges very quickly. Which means it can be an efficient way for computing the inverse. Okay. Now, you might say, but wait, the entries of M being small, M being sparse, I'm still going to have this, oh, well, I's mostly zeros as well, and then 1's on the diagonal. But wait, also in this expression, I'm mostly dealing with M here, right? Okay. All right. So then how does this work? Okay, so maybe I'll start fresh on the next page to do an example here. Okay, if our consumption matrix M is, I'm going to write this out as follows. This is 0.100, 0, 0.050, 0. Next row, 0.010, 0, 0.020, 0.025. The next row is 0, 0.080, 0, 0. Final row, 0.030, 0, 0, and 0.020. So here my entries are small, and this is sparse in the sense that like half my entries are 0. Okay. Computing I plus m squared plus m cubed plus m to the fourth and so on, I notice, of course, I might use my favorite, might use MATLAB to do this very quickly, compute these matrix powers, which is just multiplying a few matrices here, adding these together. MATLAB has no problem doing this, especially for a matrix of this size up to these powers. But I noticed that I plus m squared plus m cubed plus m to the fourth, and this same quantity, except I've also done one more step here. So here I've truncated this infinite sum to this fourth power here to this fifth power. And I've noticed that these two things match up to 4 decimal places. Which means that already this is settling down, right? Which means it is converging. It's essentially stopping at what its value is. What is this thing? So if you use your favorite matrix calculation software or otherwise to compute this, what do you get? I'm going to read this off. Row-wise here, this is 1.1112, 0.0045, 0.0556, 0.0001. Next, this would be 0.0120, 1.0017, 0.0206, and 0.0256. Next row is 0.0010. Filling this out fully so that you can see what it is that's going on here. Notice the diagonal entries are matching our experience of how they should look in these problems given what this is computing. Sorry, this is 0.0340. Here, this is 0.0001, 0.0017, and lastly 0.204. All right, so now we have this matrix looks like this. You will notice that even if you'd stopped at m to the fourth, it would have looked this same way. So it seems to have settled in on pretty much what it is. Okay, and so there is high agreement between this thing and I minus m inverse. In fact, again, up to 4 decimal places, it actually agrees. Okay, so to every decimal value shown here, this agrees with what I minus m inverse is. Okay, so this allows us to very quickly find I minus m inverse where we don't actually have to find it. We can approximate it in this way, which saves us some computation here. Okay, so you know, for example, you can just check if D is, if my external demand vector is this thing, what is the production vector, right, approximately? Well, it should be, right, P inverse, or sorry, this production vector P is approximately this thing up to m to the fifth times D, which is, if you actually multiply this thing by this vector, these are the entries that you get. You can check this yourself. And this is actually a very good approximation in this case. So you can check yourself that this is actually a good approximation. Now, what is the meaning of this? Maybe like you could have just viewed this simply as a nice computational trick. We've done some math here to show that computationally, approximately these quantities should match. So the question is, what is it that's actually going on here? Now, sometimes the answer to that is maybe not as satisfying. Sometimes it's like, well, there's this underlying structure and it works like this. It's like the question with determinants. It's like, where do you stop with the why, right? Like determinant is the way it is because the determinant is an almost unique volume or area form. It's an area computing or volume computing quantity that is essentially unique up to like a scalar. And but the underlying like reason is, well, alternating sums of dimension count like things tend to have important algebraic properties, and that's why the determinant's nice, right? It's like sometimes how satisfying the answer is really depends. But in this case, our big question is what is meant by these sums? This relationship. And again, I want to stress that oftentimes when you ask a question like this, you might not get a satisfying answer. Okay. Let's just investigate here, right? We know that when we're in the case that I minus m is invertible, then our production vector, we find that by simply multiplying our external demand vector by this inverse that we found. If we're using this formula, right, we're in the case where this thing applies. This means that P is I plus m squared plus m cubed and so on. This infinite sum times d. But let's think about what this means. Right? Okay. The original question, the whole thing I'm modeling, right, is production where I have internal demand and external demand. Right? And so what's the first thing, right? So I know that I have external demand, and I'm going to be producing that external demand, right? At least. So you could say, well, because I know that I need to produce at least the external demand, my production vector is external demand. But of course, this doesn't account for everything. This is only the external demand. It doesn't account for the internal demand. So we need to make not just enough for D, but enough to feed the internal demand. So you could say, well, maybe we need to feed like this into it as well, right? Which is I need this, okay, which is enough to feed internal demand. But maybe you say, well, I don't need to just feed external demand and some amount of internal demand. I need to feed the internal demand that feeds this previous internal demand, which is m times d, which of course is just m squared times d. And then I need to feed the internal demand that feeds this internal demand, which is, or, and so on, until all demand is fed. So, of course, what I get is this thing. Which is literally this expression. Okay, so that's one way of thinking about this. But actually, we could have thought about this in another way as well. So Thinking another way. Our Leontief input, hold on, let me rewrite this. Our Leontief input-output model looks like this, right? This is where all of this came from. So P is M times P plus D. But P is MP plus D. So P is MP plus D. But what is P? P is MP plus D. So this is M times MP plus D, which is M squared P plus MD plus D. But again, P is MP plus D, so this is M squared times MP plus D plus MD plus D, which is M cubed P plus M squared D plus MD plus D. And so I can keep going here so that this is literally I plus M squared, and so on, times D. Right? Because ultimately, in the limit, this thing, what do I get here? This thing is going to 0, and in the limit, I'm just going to get all of these M terms, right, times D. Okay, I keep doing this. The P term goes away entirely, and what is left is exactly this expression times D. Okay, so we have kind of exhausted every possible angle for this input-output stuff that we've been doing. So I think it is finally time to move on from this stuff. There's some useful MATLAB code as there are. I didn't really stress this previously when I was talking about it because I figured that you would kind of naturally see it when you're going through the notes for your homework. But each section of the notes has some helpful MATLAB code that you can have a look at if if you're unfamiliar with MATLAB, or just see a nice refresher as to some of the sorts of computations you can do in the relevant section. You can have a look at that. So the next topic that I will start on, we will definitely not finish today, but we will at least get it started, is the notion of Markov chains. So we are going to begin with a discussion of Markov chains that is, it's not going to be like the formal discussion of like the abstract notion of Markov chain, although I will talk about that after we have finished this. I'm going to begin this with a very concrete example, and then basically everything that we do from there is going to be generated by this example. So what is the idea? So the example here is that I have two states. We'll call it state 1 and state 2. The total population is 1. And the population is distributed as follows. 0.7 of the population is in state 1, and 0.3 of the population is in state 2. So 70% of the population is in state 1, 30% of the population is in state 2. Okay. Now, suppose that at the end of the year, %10 of the people in state 1 move out of state 1. Move from state 1 to state 2. And 5% of the people in state 2 move out of state 2 and into state 1. Okay. Everyone not mentioned in these moves remain in the state that they are already in. Okay. What will the new population distribution be after year's end? So what will the new population distribution be? Okay. Well, if I'm just going to write this out, right, you might automatically see how to phrase this in terms of linear algebra, but let's try to write this out just, as straightforwardly as we can here. So the first thing to say is state 1 now has how many people? It has the people that it started with minus those that are leaving, which is 10% of what it started with, plus those it's adding from state 2, which is 5% of the population of state 2. And state 2 now has the amount it started with minus those that are leaving, which is 5%, plus those that are moving from state 1, which is 10% of state 1's population. Of course, there's another way that we could write this. We can maybe be a little bit more we can maybe be a little bit more efficient here in the following way by actually combining some of these terms here, right? So for instance, you might notice even algebraically that like these terms could be combined, and these terms could be combined because they have a common 0.3 there. But what does it actually mean to combine those terms? Well, yes, you can just do the algebra, and that's fine. It doesn't need to mean anything in that sense. But also in words, it actually does mean something, because what is it that I'm doing here? It's me rewriting this in the following way. It's saying, well, 90% of people stay, right, and 10% move, and then I add some amount. So if I want to compute how many people state 1 has, 90% of people stay, so 90% times 0.7, right, so 0.9 times 0.7, and then I get 5% of state 2's population. Similarly, state 2, 95% of people stay, and I get 10% of people from state 1. So another way of writing this, if you don't like just simply combining these algebraically, state 1, 90% of people stay. So that's 90% of 0.7 plus the 5% from state 2. And then for state 2, I can say, well, I have 10% of people coming from state 1. And then I have the 95% of people that stay in state 2. This is a nicer way to write this, you might have guessed immediately, because this is a way that allows me to immediately write out a matrix equation corresponding to this, right? Now we can actually compute these things if you like. So you know, this, what is this if you actually compute this? This is 0.6450, and this is 0.3550. Okay, you'll notice that this is still distributed in such a way that the sum of these is 1. Okay, and now of course, say that this happens again the next year, right? Then you would update these values here. These would be your new values here, right? So say this happens again next year in exactly those same proportions, so that state 1 now has 90% of people stay, but 90% of the previous population of state 1, which is this 0.6450. So plus 5% of people from the new population of state 2. There it is. And state 2, I have 10% of people from state 1 plus 95% of people from state 2. And again, I could compute these and see that this is a 0.5983 and this is 0.4017. Okay, and of course this could happen year by year, right? In these same proportions, right? We can keep doing this, but obviously you have noticed by now from the form that these left-hand sides take. You have noticed what it is that's going on here, which is to recast this problem with matrices and vectors so that my population is starting with this vector 0.7 and 0.3. And it's being multiplied by a 2 by 2 matrix in this case, which I can read the entries of here. And that the resulting thing at step 1, right? So this was our step 1. This is how we started. This is our initial configuration here. So you could view this as my initial vector here. Was exactly this expression here. I'm not going to rewrite this, but what I got was that this was 0.6450 and 0.3550. So that what I really have here is that in order to get, and of course this is my next step, right? This is my population of the next year, assuming that the population distribution, which has initial values indicated by this vector, this would be the values of that population distribution for the next year. Remember, this is exactly what I expressed on the first day of lecture when I talked about matrix modeling, right? So, for instance, what I have here is an initial data vector, which I'll call x sub 0. This is my initial vector. Here I have a matrix which I will call T. Okay. And what I have here is the next time step, if you like, x sub 1. So that a way of writing this is that to get to this data vector x sub 1, I simply apply the matrix T to my initial vector x naught. Okay. You might notice something about T, namely that its columns sum to 1. Okay, that's a little special. We'll talk about that here in a second. But notice that if I wanted to go to the next step, x sub 2, what I would do is apply the same T matrix to x sub 1. And by apply, I mean multiply, of course. So, but x sub 1 is itself T times x naught. So this would be T times x naught. And exactly like I said on the first day of lecture, I can actually do this in terms of powers of T times that initial data vector. So I actually don't need any of the intermediate steps. I can actually do it from the initial vector itself. All I need is this power of T here. Okay, and in general, maybe I'll do one more. We'll say x sub 3, right, is T times x sub 2. But x sub 2 itself is T squared times x naught. And so this is T cubed times x naught. And so this shows you how to get to any nth time step. So after the nth year, for instance, in this example, x sub n is T to the n times that initial vector. So I don't need to compute any of the intermediate vectors. I actually only need to know the initial vector, but I need to know these nth powers of the matrix T. Okay. Now, this matrix T is called the transition matrix. We're going to have other names for it here soon. But the point here for this transition matrix is that this thing is telling us what is going on in regards to this initial, in this context, it's population distribution. So in the matrix T, we have columns that tell me what? The columns tell me information about where the population in the state is going to. So what do I mean by that? The first column of T tells me that 90% of people stay and 10% of people leave. In state 1. In state 2, right, what is that telling me? It's the, so how do I interpret the columns here, right, in terms of what is happening? So column J contains the information about where the population in the state J goes to. Sometimes you might refer to it as a exit vector in the context of population distribution. So it's like an exit vector from state J, and the ijth entry is going to tell me the proportion of people who moved from state J to state I in exactly one step. Okay, so, the reason why this is a little bit tricky here, and we'll see this as the matrix is bigger. This is only a 2 by 2. So you say, okay, 90% of people stay and 10% of people leave. But then here, does this mean that 5% of people stay in this and 95%? No, it's 95% stay and 5% leave. So here it's flipped. Well, it's because the entry you are talking about here, right? So maybe it makes sense to write the following thing here. So I'm going to do it here. I have room. So this can be rewritten as T sub 1, 1, T sub 1, 2, T sub 2, 1, and T sub 2, 2. Okay. What does T sub 1, 1 mean? It means the amount of people that moved from state 1 to state 1. which is to say it's the amount of people that remained in state 1. This entry is the amount of people that moved from state 1 to state 2. Okay, in one step. Now, you might say, why are you specifying that? You'll see in what we do in the future why I'm specifying one step or one iteration. This is the number of people that move from state 1 to state 2, or reading it from left to right, they move to state 2 from state 1. Okay, that's 10%. That was part of our problem. Okay, here, T sub 1, 2. This is the amount of people that move to state 1 from state 2. That's 5%. T sub 2, 2 is the amount of people that move from state 2 to state 2, or the amount of people that stayed, the proportion of people that stayed in state 2. So that is what's going on here. This is easy to confuse the first time you see this because maybe you think these sub-indices don't mean what they should. Maybe you feel like they should be reversed, but no, this is how it goes. So just to say it again, T sub 1, 1, T sub 2, 2, that's the proportion of people that are moving from state 1 to state 1. Here's the proportion of people that are moving from state 2 to state 2. There's those numbers. This is the proportion of people that are moving from state 1 to state 2 in one iteration. This is the proportion of people that are moving from state 2 to state 1 in one iteration. Okay. So the nice thing about viewing it in this way means that it's easy to generalize. To more states, right? Which means we're making this a higher dimensional problem, right? But it means that this is much easier to generalize to more states. So now if I altered this, maybe we'll just do it in the following way, right? So let's now say that we have 3 states. And I'm going to draw a diagram that indicates how the flow of people is behaving. So draw them as nodes like this. 90% of people remain in state 1. We'll say that 4% of them move to state 3. And we'll say that 6% of them move to state 2. Oh no, that's 60%. That's not 6%. Let's put it over here. Okay. For state 2, we'll say that 80% of them stay in state 2. 10% of them move to state 1. And 10% of them move to state 3. For state 3, we'll say 70% stay in state 3. 10% move to state 2. And 20% move to state 1. Should take care of everything for us. So now, what is the transition matrix for this situation? Okay, so here, this is T sub 1, 1. This is the number of people that are, it's a proportion of people that are staying in state 1. So state 1 to state 1 in one step. That's, might as well fill out the whole diagonal here. State 2 to state 2 is 0.80, and state 3 to state 3 is 0.70. So that's those entries. Now, this entry, this is the T sub 1, 2 entry, right? So T sub 1, 2 is the number of people that move to state 1 from state 2. So that's 10%. So what about the T sub 1, 3 entry? That's this one. So that's the proportion of people that move from state 3 to state 1 in a single iteration. So from state 3 to state 1, that's 0.20. In terms of the diagram, you may have noticed that I can do this row by row by looking at incoming arrows, right? So for instance, this is my T sub 2, 1. So now I'm looking at moving to state 2 from state 1. So this would be 0.06. And the other one is 0.10. Here, this would be T sub 3, 1. So I'm looking at incoming arrows here from 1. This would be 0.04. You might have also noticed another thing I could do here. And this one is incoming arrows from 2. This is 0.10. Notice that the columns sum to 1. Also, note that we call this a transition matrix, and in the context of this problem, it's obvious why, because its entries tell us exactly how these populations are moving or transitioning from one state to another. Right? So the entries keep track of how the states are interacting in terms of moving from one state to another. Okay, in one iteration. I keep saying one iteration. The reason for this is we are going to be computing powers of this transition matrix because that's how this problem is set up. And it's going to turn out that computing the powers is going to lead us essentially to considering a question of transitions involving n iterations. Right? That is what these powers are going to get us, or what is going to arise from these powers. So anyway, that's a good stopping point. So I think I will stop here, and we'll pick up with this example tomorrow. So I think that's everything. So I will see you all then. Your homework is due later today. If you have any questions about that, I didn't see any questions in chat. If you have any questions about that, let me know. I'll be on email the rest of the day. We'll have our official office hours hour this week. I'm going to post another homework that will be due next week after your first homework, but I'll give you like at least a day breather, I think makes sense. And I think that is it. So I will see you all later.